Okay, so this is question number 39 from chapter 2. And so this involves a car that's going to be driving late at night, and the driver is going to have a reaction time before they can actually start braking. There's a deer in the middle of the road, so that's why they need to brake. And we're given important information like the initial speed of the car, the distance between the starting position of the car and the deer, which is 35 meters, the reaction time of 1/2 of a second, and the maximum deceleration of the car. So because it's slowing down, meaning that the acceleration would be in the opposite direction of the velocity, that's why our acceleration is negative 10 meters per second squared. Okay, so the first part of the question is we want to find the distance between the stop position of the car and the deer when it comes to a stop. So this is when these particle models can really help simplify things. So even though I don't have exact times for each dot, and that's perfectly okay because we don't know what they are, it helps us put this problem into perspective. Okay, so I separate this question into really two parts. We have the reaction time, which is that first 1/2 of a second, and then we're going to be braking from that point. So x0 represents the starting position of the car. x1 represents where the car is after the reaction time, so 1/2 of a second later. x2 represents where the car is when it comes to a stop, and x3 is the location of the deer. So our ultimate goal is to find the distance between the stopped car and the deer. So what that's asking us to find is x3 minus x2. So this is our ultimate goal. That's what we want to find, is that position, which is represented by this the purple line over here. And so like I said, we need to break this into two parts, a reaction time part and a braking part. So for the first part, we have the reaction time, and that's what we're going to consider right now. So we know the change in time is 1/2 of a second. We know the initial position, which is x0, and we are looking for x1. So we can adapt the second kinematic equation to look like this. Where v0 is going to be our initial velocity, and then that change in time from t1 to t0, that's the time of braking. That would be the 1/2 of a second. So this is how we can find the position of the car at x1. So this is just 0 meters plus 20 meters per second, and then we multiply that by 1/2 of a second. So that gets to 10 meters. So that's how far the car moves from x0 to x1 is 10 meters. So we found the distance from x0 to x1, but remember we need to find the distance from x2 to x3. And we do not know how much time it takes to brake for the car from when it brakes to come to a stop. So the only equation that we have left to use is what I call the time independent equation, because there is no time in the equation. So we already did the reaction part. So we're just kind of considering our options here. So this is typically written as the third kinematic equation. So this is kind of in general what it looks like. Okay, and so we're going to adapt this equation. So in particular, with this equation, we're going to be considering the velocity of the car at x2, which should be 0, and its maximum velocity, which would be its initial velocity, which should be 20 meters per second. We know this is going to be minus 10. And then with the final position is going to be x2. And the initial position would be x1. Okay, so let's kind of rewrite that equation. So you could say V0 or V1. Remember, they're the same. All right. So since we're looking for this change in position here, we are going to try to isolate that. So we're going to subtract, we're going to rearrange this equation, do some algebra. Alright, so this part here is going to simplify to 0 squared minus 20 meters per second squared over 2 is minus 10 meters per second squared. And we don't know what x2 is, so that's going to be an unknown, but we know x1 is 10 meters. Alright, so moving to the next slide, that will give you 400 meters squared over second squared over minus 20 meters per second squared is equal to x2 minus 10 meters. So the left hand side will give you 20 meters. Okay, the only unit that will be left in the numerator is meters, equals x2 minus 10. So then x2 is equal to 30 meters. So 30 meters away from our starting point. So remember that x3 is equal to 35 meters. So then x3 minus x2 is just 5 meters. So they're still 5 meters away from the car and the deer. So the deer is safe. So that's good news. Yay. So in order to find the maximum velocity before hitting the deer is a little bit more tricky and more involved. So we're looking for that. We have to consider the maximum velocity really in both parts of this question. So with the braking part and with the reaction part. And so if we are finding the maximum velocity here, then remember before x2 is where the car comes to a stop, x3 is where the deer is. So in this part, that would mean that x2 and x3 would be the same thing, which would be it's 35 meters away from the initial point, which would be x0. So because we have to consider the velocity for both parts, we actually kind of want to work around this backwards, because remember that this distance from x1 to x2, or wherever the car comes to a stopping point, depends on its velocity. So, but also where x1 is depends on its velocity as well. So both of those values depend on depend on the car's initial velocity. So because of that, The reason why this part becomes more complicated is because we have to use substitution. So we have to use algebraic substitution. So if we kind of rewrite the last part of the question that we did in part A, and remember we're going to consider V2 to be where the car comes to a stop. So that would be 0 meters per second. So if we use the time-independent equation again, because we have no idea how long it's going to take the car to stop, we can solve it, but be kind of a waste of time. And so minus V0 max squared. And so we already subtracted V0 max to the left-hand side just to save us a step. 2ax. And then here is going to be, remember the x2 and x3 are the same thing in this problem. It would be x2 minus x1. Okay? And a few of these we already know. We know what V0 is, and we know what A is, and we know what x2 is. So we actually know these three variables, but there's two variables that we don't know, which is this one and this one. Okay, so let's rewrite it with the variables that we do know. So this is 0. Okay, and so I'm going to, because it's 0, I'm just going to write it for this step, and then I'll just forget about it since it doesn't mean anything. And this will be minus 20 meters per second squared. And then x2 is 35 meters minus x1. Okay, so now we need to find what x1 is. Okay, so let's actually go to the first part of the equation of part A, and the equation that we use there is actually going to come in handy here. Okay, we found this expression for x1, and that x1 is equal to the initial position plus the initial velocity times the time it takes, the reaction time, basically, which in this point is still equal to half of a second. So we can still assume that. So let's rewrite that into this, and it's going to look very similar. Okay. So x1 is equal to x0 plus v0 max, and then the difference in time from t1 to t0. Okay, that's the reaction time. Oops. And so we can simplify this equation a little bit, right? x0 is just 0, so I'm just going to kind of ignore that. So we can clean this up to equal Vmax, and then remember this is equal to 0.5 seconds. Okay, so we found this expression for x1. So what I want to do now is I want to take this expression and then put it in to this part right here. Okay, so I'm going to rewrite this equation, clean up that equation some. So minus V0 max squared is equal to minus 20 meters per second squared. And then 35 meters minus V0 max. And then that's where the 0.5 seconds goes. Sorry about that. Alright, so this still looks pretty ugly. Alright, but this is a good thing to review. is substitution. So I have v0 max in two places. I want to get them to the same side. So let's set this equation equal to 0 because we have a quadratic equation right now. Okay, so I'm going to set the left-hand side equal to 0 and essentially add v0 max to the right-hand side. So therefore we get 0 is equal to v0 max squared minus 20 meters per second squared, and meters and v0 max times 0.5. Okay, so I'm going to essentially expand on the parentheses there. Alright, so I'm going to rearrange this because what we have here is a quadratic. And I won't give you one of these on the test. Promise. That would be a little mean. And check the line above. I made an accidental error. Vmax. So, unfortunately, what we need to do now is the quadratic formula. Okay? Because I don't know how to factor that. I don't know if you do. So I'm just going to go to the quadratic formula, which is going to tell me that v0 max is equal to opposite b, which is minus 10 meters per second, plus or minus luckily a is just equal to 1. But C is minus 700. Yeah, minus 700, and then over 2, because A is also 1. Okay, so let's clean up. I'll clean up this part, so I can just say minus 5 meters per second, plus or minus. And then let's look at this radical here. So 10 squared is 100, and then minus 700 times 4. So we have 2, so negative 4 times 700 would be plus 2800. So we're going to have the square root of 2900. And then we still have our over 2 here. Okay, so using a calculator, the square root of 2900 is almost 54. It's like 53.85. And then divided by 2 is 26.93 meters per second. Alright, so let's see which one makes the most sense. Well, first off, does it make sense to have a negative velocity here? No, it doesn't. So we can go ahead and throw that out. Okay, so this minus 5 minus 26.93 meters per second doesn't make sense, so we can throw that out. So this would be the only result that makes sense. And that gives us an answer of 21.93 meters per second. That is the maximum possible velocity that the driver can have without causing harm to the deer.